In this video, I will review the definition of exponentials and logarithms, and I will explain why they are difficult to define rigorously. It may surprise you to learn that this is much harder than they told you in high school. To be fair, for most practical purposes, this is not something you have to worry about too much, but I still find it interesting to at least know that this is a difficult problem. First, let's recall the definition of logarithms that you learned in high school. When I say that the logarithm in base a of x is a number y, it means that a to the power of y equals x. For example, if I want to compute the logarithm in base 2 of 8, I am asking, which power of 2 equals 8? I can just guess, it is 3. So the logarithm in base 2 of 8 is 3. That's it. This definition is simply saying that the logarithm in base a is the inverse function of the exponential with base a. Nothing more. We can use this to define logarithm functions as long as the exponential functions are well defined. So let's review how we define exponentials, or powers. I want to define a to the c, where the exponent, c, is any real number, but the base a will only be a positive number. With a negative base, some exponents still make sense, but not all of them. For example, minus 1 to the 1/3 is the cubic root of minus 1, which is minus 1, but minus 1 to the 1/2 is the square root of minus 1, which is undefined. So we will stick with positive bases only. Let's start with rational exponents. We can break this into cases. First, the easiest case, the exponent is a positive integer. I am denoting the positive integers as z plus. When n is a positive integer, a to the n is defined as iterated multiplication. You learned this in grade 1 or 2. Second, we define a to the 1 over n, for example, a to the 1/2, a to the 1/3, and so on, as an nth root. And the nth root of a is defined implicitly by saying that its nth power is a. Since we had already defined nth power in step 1, this is a valid way to define nth root. Third, for an arbitrary positive rational n over m, we can define a to the n over m as first a to the n, and then the result of that to the 1 over m. Notice that we are using steps 1 and 2 in step 3. So far, this has defined a raised to any positive rational exponent. We define a to the 0 as 1, and finally we know how to define a power with a negative exponent in terms of a power with a positive exponent. That's it, so far no problems. We have defined any power with positive base and rational exponent. But how do we define a power when the exponent is not rational? For example, what is 2 to the pi? If you have never thought about it, this may come as a surprise. I cannot define it in terms of iterated multiplication, or roots, or quotients. It seems there is no easy way to define 2 to the pi. There is no way around it. We need to get into serious analysis territory to even say what 2 to the pi means. Here is one possible solution. We know pi has a decimal expansion, which is infinite and is not periodic. That is why pi is irrational. I do not know how to compute 2 to the pi, but I can compute 2 to the 3. I can compute 2 to the 3.1 because 3.1 is rational. I can compute 2 to the 3.14 because 3.14 is rational. I can compute 2 to the 3.141, and so on. This way I can construct a sequence of numbers, and I can declare 2 to the pi to be the limit of this sequence. This is probably the most natural way to explain what 2 to the pi means. It is also probably what early mathematicians were implicitly assuming before they started giving these problems some serious thought. But this solution is messy. How do I know that this sequence has a limit? And even if I do, there is a bigger problem. Effectively, I am approximating pi with a sequence of rational numbers. But what if I use a different sequence of rational numbers to approximate pi? Will I get the same result? The answer turns out to be yes, but it is very hard to prove. This solution may look simple, but it isn't. There are better ways. The key is to use this identity. I can write a to the c as e to the c ln a. How can this be helpful? I am writing an exponential with arbitrary base a in terms of an exponential with base e. So I have simplified the problem a little bit. I only need to worry about defining exponentials with base e rigorously, and other bases will follow. This leads to what I call the modern analysis solution. It goes in 3 steps. Step 1. Define one single function from scratch, either the exponential with base e or the natural logarithm. Of course, this is the difficult step. I will come back to it. Step 2. Define the other function as its inverse. So, if we have managed to define exponential with base e from scratch, define the natural logarithm as its inverse. And if we have managed to define the natural logarithm from scratch, define the exponential with base e as its inverse. And step 3, define other exponentials with this equation. Okay then, how do we do step 1? I have seen at least 3 different options using different areas of analysis. The first option is to use differential equations. The function e to the x is the only function that is its own derivative and that has value 1 at 0. This is called an initial value problem, which appears often in the field of differential equations. There is a result, the Picard-Lindelöf theorem, that says that a problem like this has exactly one solution. In other words, that it is okay to define a function this way. The advantage of this option is that it is very natural. It is easy to understand. We recognize this as the most important property of the number e. The disadvantage is that Picard-Lindelöf theorem is very expensive. It is a very sophisticated theorem and it is hard to prove. You could learn it in a course in ordinary differential equations. This counts as advanced math. Another option is to define e to the x as a power series. Specifically, to define e to the x with this equation. You would need the full theory of power series, not just a single theorem. You normally learn it when you study Taylor series at the end of a calculus course. A disadvantage of this option is that proving the properties of the exponential from this definition is harder. An advantage of this option is that it generalizes very easily if we want to use complex numbers rather than only real numbers. And finally, my favorite option, using integrals. Instead of defining the exponential from scratch, we can define the natural logarithm from scratch. It may feel perverse to define ln x before e to the x, but there is nothing wrong with it. We can define ln x as the integral from 1 to x of 1 over t dt. To show that this is well defined and to prove all of its properties, we only need the fundamental theorem of calculus, which you normally learn on any calculus course. Of all the options, this is by far the most accessible. A good calculus student could fill in the details. To wrap things up, my goal in this video was not to present the full rigorous construction proving all the details. Rather, as I said in the beginning, my goal was to explain why defining exponentials rigorously is difficult. I think every calculus student should understand why this is non-trivial. But if you are curious for more, if you would like to learn the details and to complete the construction, then I invite you to consider taking an analysis class.